Hello and welcome back. We're furthering our discussion in Chapter 16 in this video and specifically applying some of the concepts we've been looking at to a problem from the openstax textbook. And the one I've chosen is 16-12 from the text. It's an engineering application and it reads as the following. Each piston of an engine makes a sharp sound every other revolution of the engine. How fast is a race car going if its 8-cylinder engine emits a sound frequency of 750 hertz, given that the engine makes 2,000 revolutions per kilometer? B, how many revolutions per minute is the engine rotating through? So I've summed up the information here on the left-hand side. We're told that the engine is an 8-cylinder engine and that each cylinder makes a sharp sound every other revolution. We're also told the sound wave that is being emitted by the car is 750 hertz. That's 750 cycles or clicks per unit time. We also know that the engine goes through 2,000 revolutions for every kilometer, and each cylinder is emitting a sound for every other revolution. So that means that sound is emitted for each cylinder 1,000 sounds per kilometer. So half of this, right? For every other revolution, a cylinder emits a sound. So that's 1,000 sounds per kilometer for each cylinder. And there are 8 cylinders. So that is 8,000 sounds for every kilometer, every single cylinder, every other revolution. That gives us the number of sounds per kilometer. Then I've also defined what it is we're seeking. We want to know what is the speed of the race car. And in part B, what is the frequency of the engine? Notice I labeled that F subscript ENG to distinguish it between the other frequency of the sound wave that is being emitted by the car. This is the actual frequency of the engine itself, and we want those units to be revolutions per minute. All right, so A, we want to find the speed of the race car. Well, we know the frequency of the sound that we're hearing, how many sounds per second, and we also know the sounds per kilometer coming from the car as well. And notice that just looking at dimensional analysis, I can see that if I arrange these two values in this fashion, I will have units of kilometers per second, which is the unit for speed. So the speed of the race car is the frequency divided by the sounds per kilometer, and what we get when we convert the kilometers per second to meters per second is 93.75 meters per second. So this race car is traveling very, very fast, 93.75 meters per second. In part B, we want to know what is the frequency of rotation of the engine. So we know the number of revolutions the engine makes per kilometer. And notice that if we multiply that by the speed of the race car, that we will get units of revolutions per second. Again, using dimensional analysis here to see what way I combine these to get the correct units. So now multiplying to get rid of seconds and get minutes. So you see that the seconds will cancel when I multiply by 60 seconds is the same as 1 minute. Now we're going to have units of revolutions per minute. So taking 2,000, multiplying it by 0.09375, multiplying that by 60, dividing by 1, gives us 11.3 times 10 to the third revolutions per minute. So this gives us a real-world application for some of the stuff we've been studying in Chapter 16. In addition, it couples in some very, very effective places where we can use dimensional analysis, a very, very important tool, and a tool upon which many, many formulas have been derived. So we'll pick up here next time, continuing with our studies in Chapter 16. Thank you.